Okay, her recording in progress. Share the screen. Okay, first thing I announce is I think we're not going to have any more problems with the 40-minute limit because I went ahead and purchased a $15 unlimited time thing by myself. I had a choice of trying to get administration to do it and go through all the red tape, but that wasn't fair to you students. So I just said, forget it. I'll just pay out of my own pocket and count as a tax write-off, I suppose. So I don't think we'll have any more of that 40-minute time limit issue. But we'll see how it goes. Right, so hopefully that takes care of that. Okay, so we're on to 10.3, doing more of that today. And we'll probably get started with some of these polar graphs. Okay, schedule-wise, we have 10.3, 10.4, and 10.5 left until the exam next Friday, the 29th. Okay. All right, so let's go right to it. The homework is 1 to 11, 15 to 25, 29 to 45, 55 to 63. Let me go ahead and show that to you for those of you who don't have the book and aren't planning on getting it. So let's see, page 666 again. And whoops. And I just knocked off the screen share. So let me see if I can get back in. I think we're in, as long as I don't knock it, which might happen. Maybe I'll raise the orange here. Okay, so get that. And that. And then on page 667. And then the problems at the very end there. Okay. All right, so I did just one problem last time, and I'll do many more. And here we go. Okay, 1b, -2, 3 pi over 2. So where is the point -2, 3 pi over 2 in polar coordinates? So 3 pi over 2 is here, so I'm aiming down, but the negative means I'm walking backwards. So -r means after you get your angle, you aim at a certain angle, okay, you're ready to go that way. So if I walk in that direction, it's positive, but if I see, oh, the r is negative, then I end up going backwards. So I aim at 3 pi over 2, I'm ready to go in this direction, I'm ready to go down, but the negative means I'm walking back. So I end up over here. Okay, and they ask for two other polar coordinates, one with a positive r and one with a negative r. Well, positive r would be 2 comma pi over 2. And another one with a -2, well, how about an angle is negative pi over 2? So negative pi over 2 lands me in the same spot, and then I walk backwards. And so again, for polar coordinates, an order pair is not unique. In rectangular coordinates, it is unique, but not for polar coordinates. Okay, 3a, 2 comma 3 pi over 2. Again, the superscript, p is for polar. So I go to 3 pi over 2, and I walk down 2 units. And then they ask, what is that point in rectangular coordinates? Well, that's our ordinary 0 comma -2 in rectangular coordinates, right? We never wrote the r before because that's all we knew, rectangular coordinates. But now that we're mixing up polar and rectangular, we have to specify, am I doing polar coordinates or rectangular coordinates? Okay. B, radical 2 pi over 4. Okay, so in polar coordinates, we're doing r comma theta. But even though we're doing r theta, you start with the theta. You can't start with the r. Like if it says, okay, walk out radical 2. Well, how do I know which way to go, right? Do I go radical 2 that way or that way or that way or that way? So first you need the angle. Pi over 4, 45 degrees. Okay, so I'm aiming for that direction. And now I'm ready to walk out square root of 2. Okay, So here r is 1, r is 2, square root of 2 is somewhere here. And what is that point in normal rectangular coordinates? I use our formulas. Okay, x is r cosine theta, x is r cosine theta, y is r sine theta, right? So radical 2 cosine pi over 4 is radical 2 times radical 2 over 2, that's 1. And y is r sine theta, radical 2 sine of pi over 4. Well, sine of pi over 4 is still radical 2 over 2, so it's also 1. So this is the normal point 1, 1 that we're all familiar with in rectangular coordinates. So this funny ordered pair, radical 2 comma pi over 4, it means you go to an angle of 45 degrees, you walk out square root of 2. That's the same point as what we're used to calling 1, 1 in rectangular coordinates. Okay. Okay, 5a, negative 4, 4 in rectangular coordinates. So negative 4, 4, negative 1, 2, 3, 4, 1, 2, 3, 4. Okay, and they're asking us, what is that in polar coordinates? Okay, this looks like a 45, 45, 90 triangle, which you might recall from high school geometry. If you have an isosceles right triangle, the hypotenuse is the square root of 2 times the length of either side. So this is 4 radical 2. So my r is 4 radical 2. And what is this angle here? That looks like 135 degrees or 3 pi over 4. So 4 radical 2, 3 pi over 4 in polar coordinates lands you right here. It's the same spot that we're used to calling negative 4, 4 in rectangular coordinates. Okay, and say the same thing with a negative r. I have negative 4 radical 2, 7 pi over 4. Okay, so if you go 180 degrees off of an angle, you can have the r be negative. So 7 pi over 4 aims you over here, right? So you're ready to walk in this direction, but then I see the negative. So negative means I walk backwards. And so I walk backwards to here, and that lands me in the same spot. Okay. Okay, B, 3 comma 3 radical 3 in rectangular coordinates. What would that be in polar coordinates? Okay, so 3 radical 3, that's like 5 point something. You can put it in your calculator, but it's over here somewhere. All right, so how do I find the r? Well, I can use the fact that r squared equals x squared plus y squared. So r squared is 3 squared plus 3 radical 3 squared. 3 squared is 9. 3 radical 3 squared is 9 times 3 or 27. That gives me 36. So r is 6. That's a 6 there. Okay, then what is the angle? Well, let's see. I know from high school geometry, the side opposite the 30-degree angle is half the hypotenuse. This is 3. That's 6. So that makes this 30 degrees, which makes this angle in standard position 60 degrees or pi over 3. So 6 comma pi over 3. So the point 3 comma 3 radical 3 in rectangular coordinates is 6 comma pi over 3 in polar coordinates, meaning from standard position, you go out to an angle of 60 degrees, pi over 3, and then you walk out 6 units. Okay, and that lands me at the same spot as 3 comma 3 radical 3. Okay, and they also want another way to label the point with a negative r. So if you have 6, just go negative 6 and then go 180 degrees off. So we go 180 degrees off this way, then that would be 4 pi over 3. So negative 6 comma 4 pi over 3 is another way in polar coordinates I can label the same point. Okay. So that's what we have over there. All right. Okay, and let's see. So some other things that I wanted to show you. So we have x comma y, that's rectangular coordinates, or r comma theta in polar coordinates. So you have to say what we are now. So if I just put 2, 3, now it's ambiguous. Before, we never worried about what coordinate system we're doing. It's rectangular, right? This is x, this is y. But now that we're mixing up 2 systems, if I just write this, right? That could be polar, that could be r, and that could be theta. So if the context is not clear, that's why we're going to superscript. with either R for rectangular or P for polar. Okay. All right, so that's some of those. Now, sketch the region in the plane consisting of certain points, blah, 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 blah. Okay, so number 7, R is greater than or equal to 1. Well, R equals 1 is a circle, center of the origin and radius 1. I have a closed circle. Now, if I didn't have the line underneath it, it would be a dotted circle, sort of like you had the solid and dotted lines in your algebra course, right? Depending on whether you're including or not including the line. So you could include or exclude the circle also by making it a dotted line. So if this were R greater than 1, I would make a dotted line. Then R is greater than 1, it's everything outside. So I shade in everything out here, and R is greater than or equal to 1, just not inside. Okay, 11, R is between 2 and 3. There's no line underneath this inequality or this one. So I make dotted circles, meaning I do not include the circles there. Okay, and then between 5 pi over 3 and 7 pi over 3, 7 pi over 3 is coterminal with pi over 3. So 5 pi over 3 at 60 degrees back here. This is 2 pi or 6 pi over 3, 7 pi over 3, 60 degrees equivalent there. Okay, and I shade everything in between. Okay, so here's a description of the region. Dotted circle here, but solid line, solid because I have that and that, and then I shade everything in between. Okay. So this region is all the points where R is between 2 and 3. You're between 2 and 3 units away from the origin. And the theta is between 5 pi over 3 and 7 pi over 3. Okay. So that's about it for that one. Okay, 15 says identify the Cartesian curve. R squared equals 5. Directions there. So on top of 15, identify the curve by finding the Cartesian equation for the curve. Blah, 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 blah. Okay, well, R squared is equal to x squared plus y squared from the Pythagorean theorem. And that's a circle. Center of the origin and a radius of square root of 5. Okay, so that's it for that one. Okay, 17, there's a trick to it. It says R equals, sorry, I should say 17 star. This was not in the original, but it is similar to R17. So in fact, you could do practically the same thing. Instead of the coefficient is 2, the coefficient is 5, I see, but it's pretty much the same thing. Okay, the trick here is to multiply both sides by R. So you have R squared equals 2R cosine theta. The reason why you want to do that is because R cosine theta is another way to say X. That was one of the formulas, right? Look back on the other day, X is R cosine theta, and R squared is the same as X squared plus Y squared. Subtract 2X on both sides. So X squared minus 2X plus Y squared equals 0. By completing the square, I add 1 to both sides. Remember, completing the square, take half the coefficient of X squared. Half of -2 is -1. -1 squared is 1. So I add 1, add 1. This factors in X minus 1 squared plus Y squared equals 1. Okay, so that's a circle. Circle centered at 1, 0 and a radius of 1. So this shape, if you were to graph it properly, would be a circle centered at 1, 0 and a radius of 1. Okay, y equals 2, which we recognize as a horizontal line, 2 units above the x-axis, right? Well, all you got to do is change y to its formula, r sine theta. Y is equal to r sine theta. And then just refresh. Nothing to go over here. On page 659, x is r cosine theta, y is r sine theta. Right? Put those on your next cheat sheet. Page 660, put these on your cheat sheet. R squared equals x squared plus y squared. Tan theta equals y over x. Right? So we're using that here. All right, so r sine theta is 2. Normally, we want to write r as a function of theta. So I just divide both sides by sine theta. R equals 2 over sine theta. Sine in the denominator means cosecant in the numerator. So y equals 2, I can write r equals 2 cosecant theta. So this equation, r equals 2 cosecant theta, is the same graph, straight line, as y equals 2. Of course, this is more hidden. You can't really tell by looking at that. I can't tell just by looking at it right away without doing some analysis to figure out, oh yeah, it's the same as y equals 2. Okay, 23 is even more cryptic. Can't really tell what it means until you plug in. Y equals 1 plus 3x. We recognize that as a line with a slope of 3 and a y-intercept of 1. Okay, but how do you write it in polar coordinates? So y is r sine theta. 3 times x r cosine theta. Okay, put these together. So r sine theta minus 3r cosine theta is equal to 1. Factor out the r, and then divide by this. Okay. So this line in polar coordinates is r equals 1 over sine theta minus 3 cosine theta. Okay. So you can see it's quite clumsy to do that. Okay. All right, I think that's it. And now we're ready for the actual polar graphs. So we're going to start using our polar graph paper. Of course, I've already pre-done most of these. Sketch the curve starting with 29. Sketch the curve of the given polar equation by first sketching the graph of r as a function of theta in Cartesian coordinates. Okay, we're going to make a table. I'll tell you how I want the table to be done for graphing these guys. Okay. So some fundamentals. Again, you must use this if you want full credit. I gave you the link to it on Monday's Canvas announcements. You can find it on mathbits.com, if I can get this focused, mathbits.com. These are every 15 degrees. Sometimes that's helpful, sometimes it's not. Okay. And there are 14 concentric circles here. So if you were to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, there's 14 of them that are here. Okay. So how do we analyze these now? So 29, r equals -2 sine theta. Right, so the first thing we have to analyze, and I want you to do this analysis for every one of these graphs that we have. Okay. First, let's determine what the maximum value of r can be. Okay, I already showed it to you. Kind of put the cat out of the bag, so to speak. Let's figure this out. R equals -2 sine theta. What's the biggest r can be? Okay, I know sine of theta is stuck between -1 and 1. So if I multiply it by -2, the maximum r is 2. Now, we're going to play the game of using as much of the graph as possible, given the fact that there are 14 circles here. Okay. So if the maximum r is 2, I should not make my graph only within the first 2 circles, right? That's 2 scrunched together. That's wasting all the rest of my graph, right? Just think of regular graph paper, right? If you have regular, ordinary graph paper, you get to set the bounds that you wish, but you want to graph so that there's as much of the graph as possible, as much of the graph paper is used up as possible, but within a comfortable range. Now, there are 14 circles, so I could decide to say, well, if the maximum r is 2, I've got 14 circles, why don't I just make the 14th circle r equals 2, in which case the 7th circle is r equals 1. You can do that, but 7 is not a very nice number to work with, right? If 7 circles represents 1, each one of these is 1/7. I'm guessing most of us aren't very comfortable with 1/7, 2/7, 3/7, 4/7, 5/7, 6/7, 7/7, right? So you want to use as much of the graph as possible, but make the calculations doable. Okay, so I went with r equals 2 is the 10th circle. So my graph is only going to go as far out as the 10th circle. I'm going to waste the 11th, 12th, 13th, and 14th circle. That's reasonable enough, because if r equals 2 is 10 circles, that's reasonable. That tells me r equals 1 is the 5th circle. And that tells me any one circle is 0.2. Okay, you should show me this kind of analysis all the way through. Okay, so one more time, the maximum r is 2. I don't want to make the 14th circle r equals 2, though. That's very clumsy. So I'll make r equals 2 the 10th circle. I don't want the maximum r equals 2 just to be over here, literally 2 circles. Then you're scrunching in the entire graph here, and you're wasting all the rest of this paper, right? So a very efficient way of doing that is, okay, so the numbers come out nice. Let r equals 2 be the 10th circle. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to waste circles 11, 12, 13, 14. That's okay. Okay. And notice how I bolded in r equals 1 and r equals 2. It just makes it easier to do things. Now you might say, do I have to do that? You don't really have to, but it does literally make it easier. Okay, so I bold out r equals 1. That's 5 circles, 1, 2, 3, 4, 5. And r equals 2 is the 10th circle, and I don't need anything after that. Okay, so each individual circle here is 0.2. That's 0.2, 0.4, 0.6, 0.81, 1.2, 1.4, 1.6, 1.82, and I don't need the rest of it. All right, then I'm going to make a table. You're going to make a similar table. We'll just go every 45 degrees or pi over 4. You could get more accurate. You can go every 30 degrees. It just makes it a much longer table, and we usually don't need that much. Okay. So you set up a table, r versus theta. In general, go every 45 degrees. So 0, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. Okay, and notice I reduced every fraction that I could, right? It's sort of like a new clock where, you know, there's only 8 units and you count by pi over 4s. Pi over 4, 2 pi over 4, 3, 4, 5, 6, 7, 8 pi over 4, and the fractions are reduced. Okay, now you can go one by one, but I think it's normally much more efficient if you, I'll call it divide and conquer. That's not official. Okay, but it's a lot faster to me if you take the two extremes and then go midway, cut that in half, and then cut each of those in half, because the calculations are very, very nice. Okay? So if you want to go one by one, like do that and that and that, you can. But what I'll show you, I think, is way more efficient. You plug in 0. Sine of 0 is 0. And since I know the sign is periodic, 2 pi, I'm also at 0. All right, then I go halfway. Halfway between 0 and 2 pi. It's pi. Now, sine of pi is also 0. So that means right now, I've got that one, and that one. And then I cut those in half. So I'm going to look at pi over 2 and 3 pi over 2. So plug in pi over 2. Sine of pi over 2 is 1. 1 times negative 2 is negative 2. Plug in 3 pi over 2. Sine of 3 pi over 2 is negative 1 from trig. Negative 1 times negative 2 is 2. Okay. So cutting in half, I recommend doing the two extremes, then go in the middle, then go halfway between these, that, and then halfway between these. that. And then the ones that you have left are pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. They tend to be very, very similar. Okay, and I'll show you what I mean. First, pi over 4. Sine of pi over 4 is radical 2 over 2. It's about 0.7. So this is nice to know. Square root of 2 over 2 is about 0.707. We need that when we plot it. Okay, let's see if I can convince you of that on a calculator. Square root of 2 over 2, 0.707, whatever. Multiply by negative 2, negative 1.4. The only angles I have left are those with a reference angle of 45 degrees, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Therefore, I know I'm either going to have negative 1.4 or positive 1.4. Okay. You can pretty much just look at the chart and tell which one it is. Okay. If you're going from 0 to negative 2, negative 1.4, right? It doesn't make sense to go to positive 1.4 and then jump back down to negative 2. Okay. It almost lets you avoid a lot of trig. Okay, from negative 2 to 0. Is it going to be 1.4 or negative 1.4? Negative 1.4 seems more logical. Okay. Again, if you're doing this divide and conquer stuff, cutting in half, it makes it work a lot easier. Okay, now going from 0 to 2, 1.4 or negative 1.4? 1.4. And then if I'm going from 2 to 0, 1.4 or negative 1.4? 1.4. There we go. Right, now for the graph. 0, 0, that's the pole. And so the origin is technically called the pole. But if you want to say origin, that's fine. Okay, now at pi over 4, okay, so at 45 degrees, I'm aiming this way, but I walk back 1.4, which is 7 circles, since 0.2 is 1 circle. So I aim at 45 degrees, but I walk back 1, 2, 3, 4, 5, 6, 7. So that gives me that point. And then pi over 2, which is 90 degrees up, negative 2. So I go to 90 degrees. Okay, I'm ready to aim up, but it's a negative 2. So I walk back 1, 2, and draw that point. Then 3 pi over 4, 3 pi over 4, aiming that way, is again negative 1.4, which I know by this scheme is 7 circles. So aim this way, but I walk back 7 circles again. 1, 2, 3, 4, 5, 6, 7. And then by the time I get to pi, I'm back at the pole. So right now I got this. It is supposed to be a circle, by the way. I drew it kind of funny, but it's a circle. It looks like that's all the graph. So what happened to the rest? Well, let's check it out. 5 pi over 4, 1.4. I already have that point. It's nothing new. 3 pi over 2, 2. That's over here. I already got that point. So it just traces back all over again. 7 pi over 4, 1.4. So I'm aiming that way. I already got that point. And then 2 pi, I'm back at the pole. So I just traced my circle twice, as it were, in this particular instance. So that's r equals negative 2 sine of theta. Make it a little bit smaller so you can see the entire graph on one piece of paper. Yeah, you can get it there. But go back to that. Okay. So we analyze what's the maximum R. Then I figure out how am I going to use my graph paper so that I don't just use a tiny piece of this. And by the way, I will mark off if you take up too little of your graph. So if you just had R equals 2, so you only use literally the first 2 circles and ignore all the rest, I won't give you full credit for that. You want to space it out so you're using as much of the graph as possible. Okay, this particular graph paper has 14 circles. You know, it'd be nice sometimes to have a 15, and I'll show you some instances where we actually want to have 15 there. Okay. Okay, 33. R equals theta. Theta greater than or equal to 0. R equals theta. Okay. The radius matches the angle. Well, R and theta. I go every 45 degrees, 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, 2 pi. Okay. Notice this is pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5, 6, 7, 8 pi over 4, but I reduce the fractions as I went along. Now, if R is the same as theta, that should be pi over 4. That should be pi over 2, 3 pi over 4, and pi. But when I'm graphing over here, I need to know its decimal approximation. Okay, so I did a decimal approximation. Okay, so pi over 4 is about 0.8 to the nearest tenth. Okay, so it's pi divided by 4, 0.785, which I'm going to call 0.8. I mean, you can't get 0.785. I can't even get that accurate, right? And then pi over 2, pi divided by 2, 1.57, call it 1.6, and so on. And well, pi I already know is 3.1. And you keep going all the way to 2 pi, 6.283, I called it 6.3. Okay, so I got out to 6.3. I have 14 circles. So 14 circles, 6.3, which is almost 7. So here I decided R equals 7 is the 14th circle. Right? So I'm wasting very little. Okay, one more time. I got out to 6.3, which is almost 7. I've got 14 circles. So R equals 7 is the 14th circle, which means R equals 1 divided by 7 is the second circle, and any one individual circle is 0.5. So I went like this. R equals 1, 2 circles, 2, 3, 4, 5, 6, 7. Okay, 0, 0. Pi over 4, 0.8, which is like 1.5 circles, aiming at 45 degrees. And then at 90 degrees, pi over 2, 1.6. Okay, so here's 1, 1.5, so a little bit past 1.5, 1.6. 3 pi over 4, 2.4. Okay, so that's 1, that's 2, that's 2.5, so a little bit back off of that. And then pi, 3.1. Okay, so again, each circle is 0.5. So 1, 2, that's R is 1, 1, 2, R is 2, R is 3, and just a little bit beyond that. So it's curving like so for now. And I keep going. 5 pi over 4, 225 degrees, 3.9, so not quite 4. So that would be the eighth circle, right? So I go 1, 2, 3, 4, 5, 6, 7, 8, and back up just a tad, so maybe here. And then 270 degrees, 3 pi over 2, 4.7. Okay. So 2 of these is 1, 2, 3, 4. This is 5, so 4.7 is maybe around here. 7 pi over 4, 5.5. Okay, so 1, 2, 3, 4, 5, 6 would be over here, so 5.5 is roughly there. And then 2 pi, 6.3. I got it labeled here, 1, 2, 3, 4, 5, 6. That's 6.5, so 6.3. Okay. So it curves like this. Okay. It is a spiral shape. If you were to keep going, then as the angle increases, you just keep getting farther and farther and farther out. So this is your basic spiral. It is a spiral. This is not the only spiral. There are other equations that give you spirals, but this is a spiral. And a side note, the nice thing about polar coordinates is you can describe it very easily, r equals theta, but you never saw anything like this in rectangular coordinates, right? In rectangular coordinates, we never saw anything like that for good reason. Okay, none of the equations end up like that. Okay, you could write this r equals theta. You could change it to rectangular coordinates. It's very messy, as you might guess. It looks like a pretty messy thing, but that's that. Okay. And now for a tougher one, I'm going to call it 35 star, which is not quite the same as R35, which is r equals 3 cosine 3 theta. And what I'm doing is 4 cosine 3 theta. And it means we have to do more work. I'm doing this one because I already did it. That's okay. So 35 star, 4 sine 3 theta. So because I have a sine involved, the maximum value of r is 4. I've got 14 circles. So how about the 12th circle represents r equals 4? Okay. I will waste the 13th and 14th circle. Okay. By the way, it looks like it's more than 40 minutes, so I think it's working. So I don't think we have to worry about the 40-minute thing anymore. All right, so that means r equals 1 is a third circle, and any one circle is 0.3. Now, you know the normal period for the sine function is 2 pi. If I put a 3 in front, the period is 2 pi over 3. That means my chart's going to be 3 times as long, unfortunately. So instead of every pi over 4, I'm going to do 1/3 of that. So 1/3 of pi over 4 is pi over 12. So notice how I've broken up the table into 3 parts, and you should do likewise. I get 1 complete period after 2 pi over 3. So I'm going to count by pi over 12, starting from 0, pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12, 5, 6, 7, 8 pi over 12. And of course, I reduce the fractions as I go along. 8 pi over 12, 9 pi over 12, which is the same as 3 pi over 4, 10 pi over 12, 11 pi over 12, 12, 13, 14, 15 pi over 12, 16 pi over 12. And again, reduce every fraction. Here's another period, 2 pi over 3, 4 pi over 3. And let's see, what was this again? 13, 14, 15, 16 pi over 12, 17 pi over 12, 18, 19, 20 pi over 12, 21 pi over 12, 22 pi over 12, 23 pi over 12, 24 pi over 12. And then I reduce. Okay, this time, instead of marking every 45 degrees, I have to mark off every 15 degrees. Fortunately, this polar graph paper is divided into every 15 degrees. So that's going to be nice. Okay. If they had 2 theta, it would not be as nice. Or 4 theta, that'd be even tougher. Okay. But I'll show you how to do something like that later. Okay. So I'm using every 15 degrees this time. Ordinarily, I did every 45 degrees, pi over 4, but since there's a 3 theta there, my table is 3 times as long. Okay, so I'm going to be doing every 15 degrees, which is pi over 12. So I labeled all the way around, pi over 12, 2 pi over 12. It's just kind of a new clock. 3, 4, 5, 6 pi over 12, 7 pi over 12, 8, 9, 10, 11, 12 pi over 12, 13 pi over 12, 14, 15, 16, 17, 18 pi over 12. Notice I reduced the fraction as I went along. 19 pi over 12, that's not reducible. 20 pi over 12 is the same as 5 pi over 3. 21 pi over 12 is the same as 7 pi over 4. 22, 23, 24 pi over 12 is the same as 2 pi. Okay, divide and conquer again. Okay, so plug in 0, sine of 0, 0. At the end of one period is also 0. If I plug in 2 pi over 3, I'm taking the sine of 2 pi, which is 0. Again, I don't advise going one by one. Cut it in half. Pi over 3. Plug in pi over 3, I'm taking the sine of pi, that's 0. Cut this in half, cut this in half. So pi over 6. 3 times pi over 6 is pi over 2. Sine of pi over 2 is 1. 1 times 4 is 4. And yeah, even just what you know from trig, if this is 4, this is probably going to be negative 4. And it is halfway here. Plug in pi over 2, I'm taking the sine of 3 pi over 2, which is negative 1, times 4, negative 4. And then halfway between each of those, I'll get the angles that have a reference angle of 45 degrees. Plug in pi over 12. 3 pi over 12 is pi over 4. Sine of pi over 4 is radical 2 over 2. Multiply that at 4, it's about 2.8. Okay. So look at the pattern. 0, 2.84. How do I go from 4 to 0? 2.8. How do I go from 0 to negative 4? Negative 2.8. How do I go from negative 4 to 0? Negative 2.8. Now, I know the function's periodic. I can just copy all of these, paste, paste. Okay, except you can ignore the 0 because that's already done. But notice the rest of it, I just copy 2.8, 4, 2.8, 0, negative 2.8, negative 4, negative 2.8, 0. Same thing here. Just copy 2.8, 4, 2.8, 0, because the function's periodic. Negative 2.8, negative 4, negative 2.8, 0. Okay, so here we go. 0, 0, the pole. Pi over 12, that's 15 degrees. 2.8, that's 1, that's 2, that's 3, that's 4. So 2.8 is roughly here. Pi over 6, I'm at 4. 1, 2, 3, 4. Pi over 4, back to 2.8. Pi over 3, I come back into the pole. So here's one loop. And then I get negatives. So 5 pi over 12, I'm supposed to be aiming here, but the negative means I walk back. Okay. And then, where am I? Pi over 2, negative 4. So I'm aiming this way and I walk back to here. Then 7 pi over 12, I'm supposed to aim this way, but again, I walk backwards from here. And by the time I reach the 2 pi over 3, I'm back to the pole. Okay, keep going. 3 pi over 4, 2.8. 5 pi over 6, back to 4. 11 pi over 12, 2.8. Pi, back to 0. Nice 3 loops. Again, nice thing about polar coordinates, you get a lot of these very nice graphs that show up. I've only got up to pi. Where's the rest of the graph? Yeah, this is another situation where it just retraces itself. Okay, if I go to 13 pi over 12, which is over here, I've got negative 2.8. So I aim this way, but I walk back 2.8. Oh, I get this point all over again. And the rest of the graph is just like that. It just retraces itself. 7 pi over 6, I'm supposed to aim here. Negative 4, I walk back to there. And so it just retraces itself. And if you would keep going all the way through, you'll just see the same thing. So I get these 3 loops like so. Okay. So that's what we're up against. All right, so I was going to stop there. Tomorrow I'll do a lot more of these. It does look like we have no more problem with the 40-minute limit. What I have, so hopefully that'll be okay the rest of the way through. Okay, so let me stop the share, see if any questions you might have. Check the chat. Okay, any questions, please? All right, have a good day, and we'll see you tomorrow. Okay, all right, bye, everybody.
Take care, Professor.